In my previous video, we looked at this problem where a gas and a piston cylinder assembly undergoes expansion from state 1 over here to state 2, and it has the initial pressure and volume of 20 psi and zero point 0.5 cubic feet, and it goes to a second pressure of 5 psi and 2.5 cubic feet of volume. And we were told the process is linear, and we wanted to evaluate the work in foot-pounds in the last example, BTU. So what we had done was we first went through and we drew out all our states, and we drew out the problem. Then we went through our linear equation and we found what the coefficient of A is and what the coefficient of B is. And then we went to our equation we have for work, and we were able to solve and get a numerical number for what the work was. And that number, I'm just going to write right here, is 3,600 foot-pounds. In this video, what I'm going to show you is a quicker way to do this problem, but the requirements is the process is linear. This will not work for anything except if the process is linear. So let's get rid of all of this. I'm actually going to keep the linear process, but let's get rid of all of this. And we'll just make a note right here. This will only work if process is linear. Now, it's good to understand the last way we did things and this way, in case maybe on an exam, if you have something, you forget this equation, you're not completely stumped. You can go back to figuring out what your coefficients are, and everything should work out. But if you do remember this, for a linear process, the work is going to be equal to the average pressure times the change in volume, V2 minus V1. So this average pressure right here is really 1/2 of P2 plus P1. And what is this saying? This is just saying that I have some area under the curve. I get an average pressure, and that's what I have. So this is my work equation. Let's do this equation. So my average pressure is going to be 1/2 P2. So this order doesn't matter, but 20 plus 20 plus 5, and then this is going to be multiplied by 2.5 minus 0.5. And let's just check our units. So this is going to be 1/2. The 1/2 doesn't matter. This is going to be a, right here, this is going to be a PSI, so pounds per inches squared. And this is going to be a cubic foot. So we do have a unit mismatch. So that's why we check. We have an inch squared and a cubic feet. So what we need to do is we need to go and we need to multiply by that conversion factor of 144 square inches is equal to 1 square foot. And that right there will have right, inch squared over feet squared. This goes away, this goes away, 2 of the feet go away, and we're left with a foot-pound. So unit-wise, we're all set. So let's do this calculation. We're going to have 25 divided by 2 times 144 times 2. And we get 3,600. So right here, we have 3,600 foot-pounds. And we know this is correct. We can convert to BTU if we really wanted to, but since this is the same as right here, we know the conversion is going to be the same. So look at, why does this work? Well, if we look at what work is equal to the integral from V2 to V1 of our pressure dV. Well, the integral really just means it's going to be some area under a curve. So that's what we have right here. Well, we can break this up a little bit more, right? This is a trapezoid. So I can break this trapezoid up into two shapes. I can break it up into a triangle, and I can break it up into a square or a rectangle. And so if we could just call this 1 and we call this 2, the area of 1 is going to be 1/2 base times height. And we can, let's just call base this way. So this is going to be equal to 1/2 V2 minus V1 times my height, which is going to be, in this case, P1 minus P2. And then I can look at the area of 2. And the area of 2 is a rectangle, so it's just going to be base times height. So again, this is going to be V2 minus V1 times P1, actually just P2, right? We don't need to worry about this difference because it just goes from 0. So the total area, AT, is going to be equal to 1/2 V2 minus V1 P1 minus P2 plus V2 minus V1 times P2. Well, what can we do? Well, we can, in this case, take a V2 minus V1 out. So we'll have V2 minus V1 times 1/2, right, like that. P1 minus P2 plus P2. Okay, so simplify this. So we'll have 1/2 P1 minus 1/2 P2 plus P2. Okay, I hope you see where it's going. This right here becomes 1/2 P1 plus 1/2 P2. And then what do we get? We get, all right, this is 1/2 P1 plus P2 times V2 minus V1. We can rearrange this to get this right here is our P average. So we can rearrange that to get P average AVG times V2 minus V1, which is the equation we used for work right here. So it's just the geometric way of doing this because we are working with a trapezoid. So if you remember this process is valid only if the process that we used is valid only if the process of the thermodynamic system is linear.